Yes. So I think this is just to give it to you some time to think about. Yes, Hangzhou is a place that we need to think to go. My colleague will come soon to do the presentation. I don't know if he's here. If he's here, we can do the presentation immediately, but I prefer that just leave it with you until our plenary speaker come. Okay? Thank you very much, and I'm sorry the delay is something that is not expected. Okay? Thank you.
Plenary 2 will be starting soon. Please make your way to plenary room hall number 1. Thank you.
So, gentlemen, I think it's time to make a swap, very strategic one. As I said to you, 2025 we have IROS in China, and we have my colleague Wencheng Wang that I'd like to invite to come. Wencheng, please come to present your conference next year, okay? It's a pleasure to you. Just...
Okay. Thank you, George. I'm He Wang from Shanghai Jiao Tong University, China. On behalf of the organizing committee, I will represent the IROS 2025, which will hold in Hangzhou. We have the conference website also. The conference date is fixed from 19 to 25 October next year. So next slide. Okay, so this is our organizing team. We have the general co-chairs, Paul, Tsuya, and Torsten. The program chair was served by Igor from Steve Institute of Technology, USA. We also have Jindong, Dongjun, Qing, and Ilema for the program co-chairs. Next slide. So this is the traditional program. We have 2 days workshop tutorials. We have the 3 days main sections, and also some other activities. Next slide. So Hangzhou is one of the most important cities in China. As mentioned by Marco Polo, it's the finest and the most luxury city in the world at that time. And also, the Hangzhou have the history of more than 2,000 years. And also, it's very large city, have the population of more than 10 million. And also, there's all the saying in Chinese. Up above, there's paradise. Down here, there's Suzhou and Hangzhou. It's one of the most beautiful city. As you can see, they have the very beautiful lake. We call it West Lake. Next slide. We have many attractions. We have the West Lake. We also have the Liangzhu culture site. Okay. Liangzhu culture site have more than 5,000 years history. We also have the old street. Next slide. I don't know how to, okay. This is an attraction around the West Lakes. Next slide. And also nearby, we have the Thousand Island Lake, and also the most beautiful mountain in China. You can take the bullet train just around 2 hours. You can arrive there. And the next slide. We have many traditional cuisine in China. We have the fish from the West Lake, of course. We have many other Chinese food we will serve in our banquet. And then we also will provide some performance during our welcome reception and so on. Next slide. Also, we will demonstrate some cultural experience during our conference. Next slide. Here is the conference venue. We will hold it in the Hangzhou International Expo Center. We already blocked the whole convention center. That's the 4th floor. We also have the exhibition center. It's also very large. This is also the main venue of the G20 in 2016. Next slide. So the convention center is very close to the Hangzhou International Airport. It's only 20 minutes by taxi. And also, you can take public transportation, also very close. Next slide. This is, the conference center, we totally have more than 50 meeting rooms. We also have a very large conference hall. Next slide. That's the flight map of the totally 4 floors. We have enough meeting rooms for different arrangement. Next. And also the exhibition halls also very big. Currently, we already blocked the whole 4th floor, and we'll check whether it's enough, then we can block the whole. Next slide. So nearby, we have many hotels covered from the 5-star hotel to the budget hotels. Because the lab expenses in Hangzhou is not so expensive, so you can, with around 100 to 200 US$, you can have the 5-star hotels nearby. Next slide. And how to get there? Next slide. Actually, Hangzhou, next slide. In Hangzhou, we have some direct flight to Europe, Australia, and Middle East, and so on. Next slide. Of course, in Pudong International Airport, we have many direct flights to around the world. Actually, from the Pudong International Airport, we will provide the shuttle bus, the paid shuttle bus. Maybe within 2 hours, we can arrive at the Hangzhou International Convention Center. And also, of course, you can take the bullet train within hours. Within 1 hour, you can arrive at Hangzhou. It's very close to each other. Next slide. This movie demonstrates about the Hangzhou. That's the West Lake. I think some voice. Do you have sound? Okay, that's actually the music. That's the West Lake. That's the Chinese character of Hangzhou. That's a traditional Chinese opera. That's a traditional Chinese music instrument. Hangzhou is also very famous for the silk, Chinese silk. That's the exhibition center. That's when the G20 was held. This convention center is very close to a river, very big river. Okay, so next slide. So the IROS have been to China. The first time IROS have been to China is 2006, nearly 20 years ago. So since the China have been developed very much within these 20 years, I hope you can visit China, enjoy our conference. The theme of our conference is the Human Robotics Frontiers. We also have the conference website. Also, we have the booth. Number 29 in the exhibition area. You can go there and find some souvenirs. Thank you, and hope to meet you next year in Hangzhou. Thank you.
Thank you very much. I think it's quite interesting. So we still need some time. I think the person that is supposed to come, she didn't yet arrive. So please have a seat or maybe pick up your lunchbox. It will be interesting. That meanwhile, if you find one, okay. So please be patient, okay? So can you please just put a slide of Dr. Najwa for the photo, please? Hello? Dr. Najwa, thank you for coming. I think, please come. It's a pleasure to have you here. So let me tell you that Dr. Najwa is CEO of this very important institute in Abu Dhabi. And in fact, he's coming with a history of robotics. It was the chief researcher before. You know, she's working since a long time in cryptography, right? Security.
Yes, I'm not a roboticist, just to advertise to the room here. They're all roboticists. I'm not a roboticist myself. I'm a cryptographer slash mathematician.
I know. We know about this. And we know that it's very important to have sustainable systems. And it's quite important also to give extra lessons to us. She has a very extensive expertise on the area. And since 18 years, is working in global firms all over the world. She was a researcher.
Building trust and autonomous systems, security strategies for the next generation of robotics. Our Technology Innovation Institute CEO, Dr. Najwa is starting now. Please make your way to plenary room, hall number 1.
Someone is presenting for you, right? Okay. She was a researcher in NEC before in Princeton.
Building trust and autonomous systems, security strategies for the next generation of robotics by technology innovation.
Before joining the TI, I was vice president of Dark Markets. He has the products, cryptography, and the cybersecurity company here. But what is more important to say is that she received a recognition award for the Arab Women Awards in 2021. That's something very important. I think this is making you also special for us. Thank you, and please, it's your floor for you. Okay, thank you.
Can you hear me? First, George, thank you very much. One thing I would like to say is I'm really honored to be here, and I think I'm humbled to be here as well, amongst such a well-known community of roboticists. I can already spot some of the professors that I know, that I admire, and that I respect. Thank you for inviting me to give this session, and most importantly, thank you for waiting for me. It was not in my control. This is how much I can tell you. So what I would like to do today is two things. First thing is to introduce CII to you, and this is something that I'm very proud of. This is an organization that have joined 1 year before it was formed. And I'm very proud of the progress that it has made and also all the contributions that we have made, in particular in the robotics and the security areas. And the second part, I would like to highlight to you some of the work, the technology work that we have done in robotics, in security for robotics, and in cryptography for robotics. Before I start through the slides, I can also see a lot of TII people in the audience. I would like to thank them. This is a team that started with me from day 0 as well, and what they have done is incredible. So everything that I will show over here is not my work, is the work of the team. We have a booth outside as well. Our sister organization, Aspire, has a booth as well. So I would welcome you to go there. I will come there after the talk, and any discussion that we can have would be more than welcome. And lastly, before I start now, thank you very much for making it to Abu Dhabi. This is a city that we're very proud of the technology scene that we have today, whether we're talking about robotics, security, quantum, etc. And I would like you to see more through IROS and then through other venues, the technology advancements that are happening in Abu Dhabi and the country. So about CII, TII is the Applied Research arm of the Advanced Technology Research Council. I think I can see a lot of people in the audience that have started with us that are still outside the TII, whether they are advisors, whether they are collaborators, contributors, etc. We have started in May 2020. We're not that old. There was a decree in the formation of the Advanced Technology Research Council, and really the main aim of ATRC was to be a global R&D hub and a global exporter of technology, serving Abu Dhabi's need in terms of technology and use cases, but also becoming an R&D hub at the global scene. Aspire is the organization that supports with the program development, business development, but when it comes to the autonomous and robotics team, this is the main organization also that is organizing and leading fast mobility in the country. I'm sure you've heard of A2RL. I saw a lot of our colleagues as well around the Autonomous Racing League, whether it is with fast cars, whether it is fast drones or fast buggies. This is the organization behind that. And Venture One is the incubation and the commercialization arm. So the main aim of what we have today in TII is one, as I mentioned, position Abu Dhabi as a global R&D hub by attracting and developing global and national talent in priority research area. So let me tell you this much, is regardless of how much capital you have, how much technological assets you have, if you don't have the talent, there is not much we can do. So today we have achieved a phenomenal 1,200 or 1,250 researchers in-house. They're coming from 85 countries in the world, and they are the recipe of our success, of course, with the support and the vision of our leadership as well. Second point is we all know of Abu Dhabi Visions 2030, the commitment to the knowledge economy, the diversification of the GDP. So we would like to be a big contributor to that, to contribute to Abu Dhabi's knowledge economy through commercialization of R&D. And then finally, develop local and global partnership and create a dynamic R&D ecosystem. Today, a major also factor in the success that we have achieved is all of these partners inside the country and outside the country, and Khalifa University is one of our main partners that we could achieve success and ramp up quick. We focus on 6 priority sectors: healthcare, sustainability and energy, food and agriculture, space, security and defense, and transportation. So today, everything we do, for example, in the robotics team, and the ground vehicle team, and the marine team, etc., these are technologies that we repurpose them to serve use cases in multiple sectors. So the same autonomous car that we have developed to be working in the security and defense sector, the autonomy kit will be tailored to work with logistics vehicles, for example. The autonomy kit can be reworked for irrigation vehicles in the food and agriculture sector, and this is how we would scale. We develop the technology in an agnostic manner, and then we deploy it in multiple sectors. In terms of research centers, we have 10 research centers. 7 of them are our legacy centers that started in 2020, and then 3, the rest of the 3 are, they're newer. They started in 2022. This includes AI. I think many of you would have heard of the contribution of TII to the large language models and multimodal models and the open community with the Falcon series, and this is a success that we're very proud of and we're continuing through. Advanced material is another sector that we have where we focus on enhanced structured, additive manufacturing, cooling, coatings, etc. Autonomous robotics, you will see some of the experiments that we have today. This is a phenomenal team, not because I was leading it, just also because they are. In this team, I think a lot of contributions happened on the development of the brain and the intelligence of those robotic systems, and in some instances, we do develop the hardware itself. So we work in the aerial domain, we work in the marine domain, we work in the ground and the land domain, marine domain, on water and underwater. And we also work with single platforms and multiple platforms inside one domain and cross domains. I will show you some of the multimedia we have in a bit. We work on biotech without taking too much time on everything. We work on cryptography, developing the sovereign crypto libraries and post-quantum crypto libraries for the UAE and other work we're doing. We have a directed energy focused on high-powered lasers, the development of smart payloads, smart radars, and others, propulsion and space, quantum, I don't think I have to explain this one, renewable, sustainable energy, and secure systems. We're 1,313 members. Out of these, we have 1,250 researchers. So, there's a very big concentration, I would say, of brain power there. 256 UAE nationals, which we're very proud of. 95 advisors, I can see a lot of them in the audience, and I thank them for this. 85 nationalities. We are an applied research institute. At the same time, we contribute a lot in the community. There's lots of publications that come out of TII. I think in IROS itself, there are 6 papers that were accepted and being presented, seminars inside, outside, and most importantly, a lot of the work that we do, we see it in reality, we see it being commercialized. So today, in terms of prototypes that worked in the lab, that we're looking into the deployment and operational environment across those 10 centers, we have 131 products, and we have 65 patents in process. These are the universities we work with. A lot of them are missing from a logo perspective, but we do work with almost 100+ universities across 37 countries and with 170+ agreements and partnerships with them. So I hope I didn't bore you with the detail. It's a story that I like to tell. Now let me turn into what we're doing in autonomous robotics. Very, very brief, a high-level view on what we're doing. We're more than happy to go into the more detail with you. And what we're doing in terms of security for those robotic systems. So as I said, today we do research to serve use cases, we do research to deploy them with our clients, and we do research to go internationally. So the systems, we can use them in multiple use cases. I will give you some that we have deployed already and we supported our clients on. The first one would be for civil defense, and this is where we worked on a large search and rescue mission with civil defense authorities in the country, and also for perimeter security and threat detection. So in fact, this was a system of multiple drones, multiple cars in the ground of different types, multiple marine vehicles that coordinated on this search and rescue. In the agriculture today, we have a large engagement where we're using drones for mapping, seeding, and monitoring of mangroves. So we have repurposed all the swarm stack that we have developed in order to achieve the sustainability goals of Abu Dhabi, in order to achieve the goals of having 100 million mangroves by 2030. So this is what we're using today, not only for throwing the seeds, but also for monitoring and doing precision agriculture as well. Manufacturing, I guess this one goes without saying. We're working on manipulation arms, we're working on humanoids, and this is mainly to put those on assembly lines for tasks like welding, painting, packaging. Of course, we're still in the, let's say, the basic functionalities. Maybe we have one arm working right now. Maybe the manipulation is not as sophisticated, but this is a roadmap that we're committed to and we're continuing. Healthcare, this is not something that's mature yet, but this is where we're looking into surgical robotics, assisted in, and assistive surgical robots in invasive procedures. Logistics, the team over here is working on ground vehicles for logistics, and we do have real clients. And actually, this is public information. We're working with the ports. We have displayed it in GITEX. We have had multiple collaborations before where we're working on the automation of logistics trucks, having a fleet management system in order to coordinate and manage all these autonomy. And finally, exploration. I think there is exploration in the air, exploration in marine. There was a mission that we have conducted for underwater exploration back in April, if I'm not mistaken, and then the mission is continuing throughout the year, and also exploration in the ground domain. Let me skip this one. I think this becomes a lecture otherwise. Now, having said all of that, and this might be an area that I'm not sure how concerned any of you is. And I'm not going to take a poll of hands, but since this is a robotics community, this is a concern that will become more and more prevalent. And this is security for robotic systems. The robots are being used in more critical use cases. They're being used in critical infrastructure. The AI on those robots is something that I don't think any of us trust them at 100%. So security becomes a necessity to look at. So we have the aspect where the attack surface is being expanded. Of course, we have increased integration. So as I mentioned, critical sectors, critical infrastructure, etc. And then the robots are being interconnected, especially when we're talking about inter-domain connectivity of multiple drones, of swarm robotics, and also of inter-domain connectivity, whether we're talking about the RF connections, the sensor networks, talking back to the cloud, talking back to the command and control, there are a lot of threat vectors and the attack surface keep on increasing. Key vulnerabilities in that, it includes some of them. Some of you might think it is far-fetched, but some of them, we have seen them in our labs, and maybe they're not now something that is actively happening, but security always lags few years from the technology itself, and then it becomes a main problem. So key vulnerabilities include data manipulation, so including compromised inputs can disrupt operations and safety. So imagine this is being done in life-threatening situation, what the implications of that could be. Unauthorized access, of course, network threats, etc. So this is on the level of the robot as a system itself and at the level of the networked robots themselves. We have the risk that is associated with AI and machine learning on the robot. So basically, all of what this implies is that we need comprehensive security measures, we need secure flight controllers, and then we need a secure network on which the robots are being used, both for the data security, for communication security, and for the data processing itself. So this is a summary of what I mentioned before, including I guess the hardware security, and I guess all of you are aware of what's happening in the world, and everybody acknowledges the importance of supply chain security and hardware security per se, and this is even more relevant when it comes to robotic systems, to drone, to vehicles, etc. And today, when you just buy a robot and you want to deploy it, none of us has an end-to-end control over this supply chain. Supply chain security becomes a very important topic. Hardware threats, whether we're talking about invasive attacks like fault injections, etc., or semi-invasive ones like side channel or physical manipulation. Software threats, including software vulnerabilities that are there. And then eventually, maybe this is not something we see today, or we see it, but at a smaller scale when it comes to malware and other attacks. Man in the middle and anything that interrupts communication channel, whether we're talking about mobile networks, other connectivity channels like RF or others. All of these are real threats. All of these will happen. And you have also the additional complexity that usually those robots are dummies unless you have AI and machine learning models on top of that. So you also have the additional complexity that we need to deal with security that is related to the intelligence of the robot, including model theft attacks, invasion attacks, inversion attacks, and poisoning attacks. So from one side, we have to deal with traditional security on software and hardware and supply chain applied to those robotic systems. From the other side, we have to deal with the additional complexities of how do we deal with the models and the intelligence that is on the robot. So let me show you today what we're doing in this field. So I would like to show you two videos. One is the scenario of a search and rescue that we did in the civil defense sector. And just for you to imagine, and this is not something that we simulated, of course, that this is the future of robotics. Many of you are working on specific systems, many of you are working on specific research areas, but at the end of the day, the robotic systems are being done. All of us are putting our brain there in order to advance robotic research. They will be used in real-life scenarios. Just imagine what happens once the security of those systems, whether on device, whether on the network, and during operation is compromised. And then I would like to show you also what kind of research we're doing when it comes to the security of autonomous system and zero trust systems. So hopefully it works. Yeah. You saw this, and I think this is one of the complex scenarios that we will see being deployed in reality. And the fact is, the system before that you saw is that you have a lot of threat vectors on this system, whether we're talking about the connectivity between the swarm that you saw the mothership releasing the quads. You saw the mothership connecting to the ground station through a network, of course. You saw the ground station talking to the marine mothership, and the marine mothership basically releasing the smaller ones and then giving them the coordinates and going to the victim. If there is a weak link, or if there is a vulnerability from a security perspective on any of those interfaces, this mission could not be done, and actually it could have like disastrous repercussions on that. And this is why today in TII we have the security team, an expert of security professionals that are looking into the different attack surfaces or the different vectors, and then they're looking at how can I achieve a zero trust platform and architecture for autonomous systems, whether I'm talking about the platform itself or the network of robotics platforms and the network of these autonomous systems. So what I'll show you at the right is basically the architecture of this system, how we're thinking about the security of the robots, and then the second one is more of a detailed discussion, but it's mainly the message is the same, and I hope you do enjoy and you appreciate the work that is being done there.
And autonomous systems advance. Various autonomous systems will collaborate to perform tasks managed by other systems in a hierarchical system of systems towards full autonomic system. Future smart cities will be data-driven with technologies enabling autonomous vehicles to enhance efficiency and livability. Managing this complexity is beyond humans, and currently there's no orchestration layer for secure and safe management. This is where SSRC comes in. To replicate this intricate environment, we've developed a zero-trust-based secure platform, managing a fleet of human first responders and unmanned vehicles. From command and control to edge devices, our platform ensures end-to-end security and resilience. We began by hardening and securing our edge devices. SSRC developed secure and resilient flight and mission computers that can support any type of autonomous vehicles to mitigate a wide variety of threats and attacks. Communication among devices and command and control is secured through radio-agnostic, secure communication shield, facilitating mesh communication for short distances and long-range communication for distant devices. Our secure flight and mission operations, FMO, serve as the command and control center, orchestrating and managing the autonomous entities securely. Operating on zero-trust principles mandates that every device within the environment continuously engages in mutual verification and authentication of identity with other devices. This procedure is facilitated by commissioning devices in the factory, where birth certificates are issued from a secure facility. Subsequently, these certificates are provisioned and verified to ensure the identification and validation of devices ready to be deployed. SSRC is also developing a GNAI-based secure runtime assurance, which enables devices to collaborate with each other in real time to enable security, resilience, and safety in autonomous systems. This end-to-end solution is operational and can serve a wide variety of use cases like military, civil defense, logistics, and many more to enable security, resilience, and safety. TII innovation for a better world.
Okay. I think with this, I would have given you, I hope, an overview about what we're doing in the autonomous center, complemented with all the security systems and security architectures we have. I would welcome to get any questions myself or the team that is present around today in order to get questions on what we're doing, on TII, etc. I would like to thank you for your time. Again, I apologize for the delay, and I hope to see you outside. Thank you very much.
So, Najwa, it's neither a problem. It's also let's say, a good time to have you here. Let me, before you start for the questions here, Najwa, it will be interesting to know something. You know, you're looking for robotic for sustainability. Something is very important. We need to have robots operating there outside, helping people. Can you just share with us how important to have robust systems to help us to make our world a little better, please?
Sure. So today, George, as I said, the robotic systems that we are doing them are not staying in the lab. We're deploying them outside. We're deploying them in many scenarios. So let me give some examples. You saw search and rescue missions that we are doing with the civil authorities for rescue missions in the water or rescue missions deep in the desert or in the land. Other robotic systems that we are deploying, as I mentioned, are for the sustainability environment overall. So whether it's the drones that we're using for seeding mangroves or the likes, whether it is the marine robotics systems that we are using for coral reefs restoration, for pearl beds restoration, whether it is actually the ground vehicles we're using for irrigations and deep irrigations in the desert or in forests, etc. We're also working on systems for monitoring of disasters and also for fast emergency responses. So this is also where we're putting all the robotic systems in there. Assistive robotics is very important. So looking into how can you have humanoids, how can you have manipulation arms, manipulation wires in order to do assistive robotics. So this is just, just touching the surface. This is the peel. But robotics today, if it is well architected, well engineered, and you have the right AI and intelligence on top across all the robotic stack, can be used for the good of the society.
Yes, I think it's a time of opportunities here, right?
Absolutely.
Okay, thank you. Please, audience, we have questions for Dr. Najwa? No questions?
Either everybody was bored.
Sorry?
Either everybody was bored, or there's a question there.
Thank you, Dr. Arash. I'd like to ask you about your opinion on the timeline on the end-to-end supply chain independence in the Emirates.
Sorry, I couldn't hear you. I apologize.
In your opinion, what is the timeline on the end-to-end supply chain independence in the Emirates if it hasn't already been achieved?
This is a good question, right? Without having to dissect the robot today, but from a software, let's say from a software intelligence perspective, this is something that you see that TII and Khalifa University and other players that are working on the development of that. You also have a lot of hardware, robotic system hardware developers and manufacturers, even OEMs in the country, right? Of course, you still have dependencies on the sensor payload, on the chipsets that you have, on the GPUs that you have. This is where there is dependency on the supply chain from outside. So there is a mix. Of course, we're ramping up on all of these capabilities, but today we have a mix of supply chain, let's say, origin in the UAE.
Okay, thank you very much. Any other question? Najwa, you recover the time.
Thank you, George.
So I think if you no other questions, just, yeah, you have a question in the back. Please, I think the only way to reach you is
Hello, Dr. Najwa. Very nice to have you here. Just if you can share any collaboration between the AI Center and the Robotics Center on large language model for robotics, if there is any project going on. I don't know if you can.
Can only expect this question from you, Eliseo, right? Okay, it's actually a very good question. Today, whatever you've seen does not have LLM yet. But indeed, it's a very good question in the sense that we are exploring how large language models and multimodal models can be used in the robotic systems. We are exploring multiple avenues today, including how do you do mission planning, how do you use them for organizing hierarchical trees or systems and swarms, and of course, when it comes to humanoids and manipulation, this is where we're using LLMs, VLAs, and looking into the Gen AI areas, and there will be many other venues, but these are the main areas of focus in the research front that we are looking at today.
Thank you. I think just tell we have a specific plenary discussion also about this tomorrow. Okay. Anyway, Gregory.
Hi. Thanks very much for that great talk. My question follows very nicely from what you just mentioned. It's about LLMs and foundation models. My sense is that they're going to be the secret to the generalization and robustification of a lot of robotics going forward. And yet I think we're seeing a lot of concentration of power as a function of how hard and expensive it is to train modern foundation models. I think UAE is actually possibly well positioned to play in that game. I just was wondering what your perspective is on how this trade-off between a small, extremely expensive set of foundation models versus the academic world is going to play out. And in some sense, in terms of building foundation models from the ground up, that becomes an enterprise that most universities can no longer do. And so do you have a sense of how the balance between super big expensive models and the rest of the community is going to play out, especially here in UAE?
Okay, I'm sorry, there's a bit of sound issues, but let me repeat your question if I got it right, and I will answer. You're asking about how do we strike the model between excessive training of more expensive models and putting them on the drones, and let's say lighter networks that we train and put them on the drone, right?
No, that's a great
no.
question,
Okay.
but it's not my question. I'm
Yes,
going to run up
please,
here
yes.
and say it to you, and
That's
you can repeat
easier.
it.
That's easier.
Foundation models are super expensive to build.
Yes.
And only a small number of organizations can afford to build them. And so the power of the foundation model world is in some sense in the hands of a very small set of companies, like OpenAI, maybe it'll be Khalifa. You have a sense for how this will play out? Like, can we all compete in this world, or do we all have to be at the mercy of OpenAI and Meta?
Yep. I think I have your solution here. Sorry, I couldn't hear you. So this is a good point. It's a bit of, I guess, complementary to this. Today, as an organization, us as TII, we acknowledge the fact that, in 2022, November, when ChatGPT was out, there was this, let's say, mercy of OpenAI. Having said that, you see a lot of models that are being open sourced today, that they are being out there on GitHub, on Hugging Face, etc. And then the community, the research community, even the industrial community can pick up. One of these models is something that came out of the vision of our leadership, is that we want to invest in very good and actually top-performant large language models, and later on multimodal models, and then open source them. And this is where Falcon was born. So today, if you see TII Falcon, this is a very successful one. It came, on top of the leaderboard of Hugging Face, starting from the version that was released in 2023 with 40B to 180B, and these were only text. Then we had released in February the Falcon 2 11B, which is multimodal, all based on the transformer architecture. We even open sourced the one with the Mamba or the state space machine architecture, right? So, and the main aim is what you said. Today, for you to have this much compute, to have this much data in order to train them, you need resources behind that, right? Which from our side, we had that. But in order to democratize and give access to those communities that don't have them, we open sourced it. We even put together the Falcon Foundation in order to support companies with compute, in order to support them with the use cases, etc. And this is the philosophy of what we want to do with our foundational models. Now, that doesn't mean that we will not use them for our own commercial use, right? So for example, what I discussed before, quantizing the model in order to be used on the edge is something we're doing, and we will be using it for robots. Developing VLAs that can run, I don't know, on Thor, on Orion, whatever, and putting it in a humanoid is something we are doing. From one side, there is the open source philosophy to get access to this model. And 180B is a very, very big model, right? I think it was 3.5 trillions of tokens that it was used. It's a very big model. We open sourced it. From one side, it gives access. From another side, it increased trust, trustworthiness, etc. of the model. And whoever wants to leverage this commercially can. Then you have the foundation, which is even supporting beyond the, let's say, the model itself. It's supporting with use cases. It's supporting with in implementation, etc. I hope I answered your question. Great.
I think we never stop the answers, questions, because
Great.
we are evolving, right? Thank you very much,
Thank
colleagues.
You.
Thank you, Najwa, also to
Thank
come.
you very much.
And I think it's time to close now. Thank you very much. So it's time now to pick up a lunch. Yes, thank you. So we quit now.
seems not to be working.
Yeah, I have not even tried opening Acrobat.
Because I organized this thing about the satellite conference centers.
I see.
So people want to log in from far away, including Indonesia.
Yeah.
And it seems to be problematic. Yesterday I couldn't see anything. I want to see the keynotes, the panel report.
Okay, shall we start?
Good afternoon, everyone, and also a warm welcome from my side to IROS 2024. I'm Helge Wiedemann, I'm from University College London, and I will be your host today for the keynote session on biorobotics. We have 4 distinguished speakers who are pioneers and thought leaders in the field of biorobotics. Their groundbreaking work has been featured and published in many top-tier journals in the field of robotics and beyond, earning widespread recognitions and prestigious awards for their achievements. First up is the head of the Biorobotics laboratory at EPFL, talking about biorobotics computational neuroscience. Please welcome Octopus-inspired.
Great. Can you hear me properly? I like to move a bit, so if you don't mind, I will do it like this. So, first of all, thanks a lot to Cecilia and Jorge for inviting me to here today. I'm really honored to be here. And I'll try to show a bit how robotics can be useful to study animal locomotion. I love animals, and I think robots can be useful for studying animals. If you watch this movie here, you can see the beauty of animal locomotion. And this is really a superb control problem that they're solving, a very complex control problem. If you see the fact that they can move without falling, is really thanks to a very good nervous system that can handle the high degrees of freedom, the non-linearities of the system, and the instabilities of the system. And I'm really impressed by how animals can do this so beautifully. And I think that robotics can be useful to investigate how this works. So I think we're living exciting times in robotics. There are beautiful things happening in terms of biomimetic robots and soft robots being there. Deep reinforcement learning progressing very fast. Also commercial robots that we can buy, Lego robots. And also the simulators and the fact that we are now often in high-impact journals. So I think that's all very exciting. And neuroscience is also having a boom. So the fact that there are transgenic salamanders and transgenic animals, you can now really identify neurons genetically. You can get the whole connectomes, and you can also get access to them through optogenetics to modify, activate, deactivate behavior during neurons during behaviors. And of course, simulation is making progress. So I think there's really a beautiful interaction that can take place between robotics and neuroscience, addressing some key questions. So what are the big questions? First of all, I think we still need to work on understanding the principles of animal locomotion. How do the different components interact? Secondly, I'd like to explore how the control has adapted to multiple morphologies. So if you look at evolution, it's impressive all the modes of locomotion that we see. That's also an important question to address. And learning. How do animals learn, improve over time? How do they plan? Is also an open question. And when you think about it, it's impressive how good animals are, given that they use very slow computational elements. Neurons transmit information very slowly, 100 meters per second, orders of magnitude slower than control loops in a robot. And therefore, nature has invented a multi-layer control architecture, giving a lot of importance to the body dynamics. And then the spinal cord is super important. So the spinal cord in vertebrates has multiple reflexes, providing feedback loops. And these very interesting circuits called central pattern generators. These are networks in the spinal cord that can oscillate by themselves, and that are kind of feed-forward controllers at the level of the spinal cord themselves. And finally, you have higher levels of control, multi-layers on top of that, supraspinally in the brain, that use internal models to do also feedback and feed-forward control. And I think this is a very interesting control architecture when you have slow components. And I like this image of Jerry Lubb, which sees the spinal cord and the musculoskeletal system as a puppet on strings, where playing with a finite set of strings, you can modulate and generate complex behavior. And that's something I like to investigate. And one thing I find interesting as well is the fact that all these different animals have more or less exactly the same control architecture. Same reflexes, same central pattern generators, same descending modulations. And I find it really fascinating how the same neural architecture can be used to control so many different morphologies. And it looks like evolution has found a very good way to rapidly download the control in a new body to explore new modes of locomotion. And I think that's interesting. Now, this neural control architecture has changed still a bit during evolution. And we have the hypothesis with Monica Daly that lower vertebrates are more driven by the spinal cord circuits, and especially by the central pattern generators. And the more you go to unstable locomotion, the more descending modulation and feedback plays a role. And these are exactly questions which, as roboticists, we are used to address. So we can use robotics tool to investigate these control loops, make prediction, and test them using simulations and robots. So let me show you the salamander, which, as you probably know, is one of my favorite animals, because we have been studying it for quite a while with colleagues in biology to see how the spinal cord is organized to control the gaits of the salamander. So here what you see is a salamander robot that's completely driven by a model of the spinal cord of the salamander, especially of the central pattern generators. And I think what's interesting here is the beauty of locomotion with just two descending drive. Two strings to the puppet are sufficient to modulate speed, heading, and type of gait. And it's really the central pattern generator that's completely in charge of the high dimensionality that you need to send to the actuators. And interestingly, this is open loop. So this is really feed-forward control. The CPG doesn't receive feedback. It just receives input from the high-level control, which is like a remote control. Obviously, there's feedback in the system, even in lower vertebrates, lots of feedback. And another question we had is to see the importance of feedback. And here we went to study the eel, which is a very impressive animal. It's super robust. The fact that you can do one transection or even two in the spinal cord and still have intact locomotion. So if you have half an hour after these transections, the eel will swim as if nothing had happened, while in most animals this would be really dramatic. You'll be tetraplegic or paraplegic. So it looks like the animal has an intrinsic robustness which is quite incredible. And there must be some mechanism below the transections to allow to keep the rhythms active and synchronized. So here again, to study this, it's interesting to make models. And here is what we did. We tried to model all the components, the oscillators, the coupling, the feedback. And we focused a lot on feedback from tactile sensing. So we equipped the robot with very primitive skins, with little load cells. And we're interested in seeing how that feedback affects the local oscillators, because we know that fish have exactly that type of feedback. And then, scientifically, what's interesting is we know that the animal has a complete circuit, as you see here on the top, right? But we can systematically investigate if you activate or deactivate some component, what happens. And possibly, the most interesting result of that paper was when we're removing all coupling in the system, like an extreme example of transections in the spinal cord. And this is what happens. So imagine you have the local oscillators here. They have no idea what their neighbors are doing. They only feel the water. And that local feedback loop is sufficient to generate beautiful emergent gaits that are stable and that are very close to the optimal speed you can do at that frequency. And that's quite striking. I think I was impressed by that. I was not expecting as good swimming. And this is probably why the eel is so robust. The feedback, the very local feedback, is sufficient to stabilize completely the locomotion. Now, adding the coupling makes it better. So if you have the coupling, you have much faster acceleration, no short transients, and you are much more robust against other perturbations. So it's still good to combine feed forward and feedback control. But still, I was impressed by how the feedback could play this big role in stabilizing locomotion. What about learning and planning? So here is another project where we want to see how high part of the brain can modulate what happens in the spinal cord. And I think this is an interesting question which is a bit understudied. The fact that we don't know yet in neuroscience how the descending modulation affects locomotion and behavior, because except maybe for muscle fingers, there's no direct connection from the cortex to the spinal cord. Everything goes, from the cortex to the muscles. Everything goes through the spinal cord. And therefore, when we plan movements, like now I'm locomoting, I'm planning my steps. If I go jogging, I'm planning behavior. I do that in a very strange input space where I activate some descending signals which will activate rhythms. Others will change the postures. Some descending pathway will inhibit reflexes or augment them. It's a very strange space in which to do planning and learning. And therefore, to explore that space, we use deep reinforcement learning. So a simple multi-layer neural network that will play the part of the brain as a policy. And then we wanted to see, could we learn to modulate locomotion extensively? Have omnidirectional steering, changes of posture, all the kind of things you need for high-level behavior. And there, what's interesting is we try that on the robot, and we then have all the sensory streams that animals have, and we can do systematic testing of which of these feedbacks are important. And from a deeper reinforcement learning point of view, what's very interesting is we only needed 3 terms in the reward function. Normally, you have like 20 terms in a complex reward. Here, just 3 terms were sufficient to generate complex behavior with nice omnidirectional steering, as you can see here. So basically, that shows that there was no problem at all for the higher policy to nicely drive the locomotion at the spinal cord level. Another good feature was the sim-to-real transfer, which was surprisingly easy and robust. So almost without any randomization during training, you can apply this to the real platform. And even sometimes without even randomizing the environment, you have robust policies that can run on the real platform. So the sim-to-real seems also to be simplified by the spinal cord circuits. And finally, what we did is then more systematically explore how feedback is used, possibly, in the animal. We found, for instance, that load contact is super important. And we also looked into vision to see how animals can do anticipation. And here, obviously, what's important is, if you go running, is to know in advance where to place your feet, to adapt your gaits. And the policy is perfectly capable of doing this anticipation. More than that, we were able to try to reverse engineer what are good criteria to optimize when you do gait transitions. And it looks like viability, not falling, is one of the best things you can do, not only with irregular terrain, but also on flat terrain. And finally, almost finished, we now look into more complex behaviors to see how we can do some kind of parkours like this, complex terrain. And for me, one of the most exciting results here is if we add delays in the loop, we can do very well, surprisingly well. So again, coming back to the reason of having multi-layered control, looks like one of the reasons is to have this high stability. And here I want to advertise the talk of Sun. It will be the last talk for the conference on Friday. I hope you're still there. He will present this in more detail. And finally, ongoing work to address the question of multimorphologies. We got excited by that, and now we have a bit of a challenge to see, could we download our policy in multiple morphologies, have multiple locomotion? For quadrupeds, we can cover many of them, and now with Milad and Guillaume, we even try salamanders, bipeds. It's not there perfectly, but it looks like the same policy could very rapidly be adapted to very different morphologies. All right, take-home messages. So first of all, the nervous system is beautiful, multi-layered, very nice combination of feed-forward and feedback. It looks like these different components have a bit change of role during evolution. But still, I'm impressed by how conserved it is and how easy is it to control a very large diversity of morphologies and modes of locomotion. And finally, you can do learning on top of that. And I think there are many more opportunities to combine neuroscience and robotics and have fruitful interactions. So that's it. I'd like to thank the people, the funding, don't miss these presentations tomorrow and on Friday, and thanks a lot for your attention.
Thank you very much, Auke, for sharing this very exciting intersection between neuroscience and robotics. And we will continue with some exciting presentations because we have here the director of the Bio-inspired Soft Robotic Lab from the Italian Institute of Technology. And she will talk about bio-inspired soft robots. Please welcome Barbara Manzolai.
Thank you. Thank you. Good afternoon to everyone. Thank you, Helge, for the kind introduction. I'm very pleased to be part of this session by Robotics. And I would like to start by introducing our approach to the field, which is deeply based on bioinspiration. So our approach is to select some biological models and some features that we consider relevant for developing new robots. So we transfer and translate such features into specification to develop a robot that can operate in a complex environment and can cope with uncertainty. And this is why bioinspiration, in particular, we are developing robots that can be used for environmental monitoring or precision agriculture and also exploration. At the same time, sometimes, as Auke already explained, and so we can use these robots, this platform, to validate hypotheses in biology. So it's a double goal to validate hypotheses in science, but also to make innovation. But you know, most of the robots in this field are inspired by animals, as we already seen, for the locomotion, for the learning, the communication, for many other aspects. So the point is that I would like to share with you, can plants be considered as a model in robotics? So, you know, very often we consider plants as a passive organism, not able to move, to communicate, to perceive the environment. So, the question is, do plants move? Yes, they do. They do in a very efficient way. So, they move continuously by growing at the apical region and both in the shoots, in the roots. So, they add new cells by cell division and they change the morphology on the basis of the external stimuli, so they show very high plasticity. There are also very fast movements in plants, like for carnivorous plants, they close, for example, in Dionea muscipula, they close the leaves in less than 1 second when there is a prey inside the leaves. So, yes, they move. And the second question, yes, what is the problem in particular is the time scale. So the problem that we have with the plants is that we cannot perceive the movements because they are too fast or too slow for us. So like in the Utricularia australis is one of the fastest movements in nature, but we need to decelerate, otherwise we can observe, or accelerate, like in the case of the roots. So this is the point. But the second question is, do plants sense? So yes, they do. And the movements are not a random movement, but they are guided by the perception of the external environments. And so these kind of movements are called tropism. So they can move towards or far from environmental stimuli. And so they, perceive and then take a decision in the direction of growth. So they are very complex, the decision, because they can perceive several stimuli at the same time, so chemical and physical parameters. And then, so the last question, but I think that now you know the answer. So do plants communicate? Yes, they do. So, of course, in a different way, but they create, for example, underground networks, and they communicate. So there is a communication plant to plant mediated by fungi. They release a message, in fact, in the soil. They are perceived by plants, and they establish this network underground for the communication. And also, they emit volatile in air, but they also are based, the communication are also based on fast communication with electrical signals. So also they communicate. And so the goal is, in fact, to consider plants as a modern robotics. In fact, they are simply different. So they can move without muscle. They take a decision without a brain. They can communicate. So they have this indeterminate growth that means that they grow for the entire life. Show very high plasticity, so they're changing continuously the behavior and the morphology on the basis of the external environment. And our idea to take inspiration from this system to create a new strategies of movement, of control, and also materials and communication, but also a solution to save energy during the movement. And I would like to present 3 cases. In particular, movement in climbing plants based on the growth that I mentioned before and the tropism, but also anchoring strategies and actuation based again on systems like tendrils and passive movement for dissemination of seeds into the environment. So first of all, climbing plants as a model. These are quite peculiar plants because they use most of the energy that they have not to create a trunk, a robust trunk, but to grow faster with respect to the other plants towards the light. So they establish a competition with the other plants, and in order to avoid to collapse under their weight, they need to anchor, they need to sustain the body. So they create this twining movement around the support. They also create tendrils or spines, dizzy pads, and so on. And so all this solution can be transferred in technology. They also explore the environment without vision by implementing this circuitation. This is the name. So very large movement to find the support and then to anchor. And very important, as I say, that they can climb. So our idea is to transfer this concept of growing in robotics by developing a 3D printed machine inside the head of the robot. It's a miniaturized 3D printed machine. So the mechanism is very similar to the additive manufacturing approach. So there is a motor in the head of the robot that pulls a filament from you see a spool, a thermoplastic material. The material enters inside the head of the robot where there is a resistor, so increases the temperature. The material becomes sticky and the new layer can adhere to the previous one. So the robot is able to create its own body layer by layer. So we don't know a priori the morphology of the robot because it really depends on the external environment and the external parameter perceived by the robot. In the head there are sensors for different parameters, and there is an algorithm based on the tropism behavior integrated in a microcontroller also in the head. So the robot can grow, but very interesting, can also bend like a real plant by a differential growing. So we can control the deposition of the material by tuning the speed of the motor. And so we can have different, same layers, for example, in the recent control strategy, but different height of the layers by stretching the material, so by play with the velocity of the motor. Also very interesting, we can implement this twining behavior to climb around the support, and then depending on the sensor integrating the tip, the robot can be used for exploration, for example, environmental monitoring. What we know from literature, from biology, is that climbing plants need to perceive gravity in order to implement such a twining behavior. In fact, in mutants, without the gravity cells, they are no more able to climb or to move upward. So we implement the gravity perception also in our robot with a 3-axis accelerometer in the head again. And by controlling the angle generated by the projection, the gravity vector on the XY plane, and the direction of the material deposition, we can sect the behavior. In particular, in order to have this twining around the support, we need an angle of 90 degrees. But then we can play with 0, 90 or 90, 180 degree to have a bending or different radius for the movement. Not only the movement, what is also interest in taking inspiration from the plants is implementing a different kind of behavior based on, again, on the perception. Of course, the plants, climbing plants also perceive light at different wavelengths, and our idea is to imitate the behavior, especially of the young climbing plants when they are in the forest, because they cannot perceive directly the light, so they perceive a shade. And so there is another tropism called scototropism, but they also perceive the presence of a plant in the surrounding by the perception of the ratio between red and infrared. So they move towards the plant, then they climb, and when they perceive a light, they switch to phototropism. And this is exactly the behavior that we have implemented in this recent version of the robot. Also, we can give a higher priority to the robot to follow the shade. And so this is very convenient, especially in a structural environment when the robot cannot perceive a light or other stimuli, so it can move to this direction, then switch to another feedback, another stimulus if necessary. So these are the robots. We can tune also the temperature of the plotting and the feeding in order to have different mechanical properties of the robot, especially when it has to overcome voids, needed to have a stiffer body and structure. But as I mentioned, they can also create tendrils to anchor. This is another strategy. And what I would like to mention for plants is that they don't have a muscle. So in order to increase the stiffness, they cannot contract the muscle. But they can play with the water content in order to generate a stiffness, so to generate a turgor. And this is based on osmosis principle, so the movement of flow of water in the direction higher ionic concentration. And so there are many movements based, in fact, on this flow of water. And we also develop a tendril-like soft robot in which we have a completely soft body with an osmotic membrane, soft electrodes, and ions in the liquid. So when we apply a very low voltage to the electrodes, there is an ion absorption with a consequent movement of water in the direction of higher ionic concentration. And this generates a turgor, so increases the stiffness of the arm. Instead, when we remove the voltage, of course, we have the opposite movement. And so this movement is reversible and reversible. No, sorry, doesn't work. Okay, it worked. So there is this coiling and uncoiling mechanism of the tendril, so it's reversible, and we can play, in fact, with the water content in order to have a stiffness inside the soft body, also without, in fact, a muscle. And finally, I would like to mention this kind of movements in plants because they are quite peculiar. They are called, try again. They are, oh, okay. So they are called passive movement because there are, try again because it's important to show. Okay, it worked. So this kind of movement are called passive because there is no metabolism in these structures. So these are fluids that transport the seeds into the environment. But actually, they continue to move, so there are active movements thanks to the arrangement of the materials in the cell wall. So there are some active material that reply to the humidity variation into the environment, and other materials that play the movement depending on the geometry, the arrangement of the fibers. And our idea is to take inspiration from these structures, from this movement without metabolism, to generate soft robots, completely biodegradable, covered with nanoparticles, also biodegradable, sensitive to different parameters into the environment, temperature, humidity, CO2, mercury, for example, that is a pollutant. When these nanoparticles are excited by laser beams on board the drones, They emit a fluorescence, and the fluorescence is read by LiDAR techniques on board the drone. So in this way, we can release tens of these robots without affecting the quality of the environment, and at the same time, completely avoiding the presence of battery and electronics. Just to show you the approach, so the idea is to imitate such arrangement. So we started from biology, and we investigated the ultrastructure. So in blue, there is a cellulose layer, the active layer that replies to humidity variation into the environment. And in yellow, there are fibers of lignin that, again, depending on the angle, they generate a movement. To explain this concept of the importance of geometry in developing this kind of robots, we developed mock-ups made by PCL, soft material with a PO that is hygromorphic material. And what we change is just the angle generated by these fibers. And so we can observe completely different movements, so bending, torsion, coiling, just changing the angle. And so the idea is to create these soft robots that can move by coiling and uncoiling, so perception with the environment, in particular humidity variation. Randomly, they find a crack, like the natural seed, so there is no need of additional control. The control is in the design, at the design level, and they move to explore the environment. Not only drilling, also flying seed. This is the case of the Samara. So we, again, you know the approach. So we started from biology, the ultra structure of this seed, this fruit actually, and then we replicate by developing this soft biodegradable robot based on additive manufacturing approach that can in fact be then covered with nanoparticles, as I mentioned before, sensitive to laser beam in order to emit fluorescence. And the idea is, in fact, to, I try again to show you that, okay. There are drones, of course, that can release the seed into the environment, and then also other drones that are used for geolocalization of the robot and also for reading the fluorescence emitted by the robot. And finally, this is also a very recent result in which we develop an hybrid system, so not only fully artificial. We can use the own of the Avena because they are really fast in reply to humidity variation, and we generate an artificial capsule based on the natural one that we reconstruct by micro-CT analysis. So we use it for creating the molding and generating the artificial capsule. That then the idea is to fill with natural seed for reforestation. And so you can see the natural and the hybrid system that move. So the hybrid system now doesn't move, but it should. And I try again, but just to say that are very, of course, we use the owns of the Avena, and so also the hybrid system can move in the same way. And the idea is exactly to use for germination, so you can see the plants, but by the way, you can understand the concept. So they can germinate by using this approach. So to conclude, I mean, I hope that I convince you that plants can move. They move in a different way. They don't have a muscle, but they can also generate a very fast movement, in fact. They perceive the environment, they take a decision on the basis of this feedback, and consider that they perceive many stimuli at the same time. So it's not a simple reply, but they have to take a decision on the basis of the priority that they give to the stimulus, and also on the basis of the internal needs. So exploration without vision. They are based on, many of these movements are based on programmed passive movements. They save energy during this movement, so these are very interesting also for new solutions for implementing frugal energy strategies, and they are efficient in the communication. Moreover, nature can also provide us with a new idea for developing more sustainable robots, introducing this concept of cycle life into robotic. The idea is, in fact, to have robots that can help humans and can interact safely with the humans and other living organisms without causing any damage to the environment. At the same time, can be used to protect natural resources, but then at the end of the life cycle, they disappear because they are reusable or biodegradable. And so there are many challenges, of course, that we have to face scientifically, technologically, maybe we discuss later on. And so with this, of course, I would like to thank my colleagues and all of you for your kind attention. Thank you so much.
Thank you very much, Barbara, for showing us this amazing work where you engineer robotic solution to capture the capability of plants that have sensing capabilities, that have growing capabilities, and even communication capabilities. So thank you very much for this. And we will continue with translating nature. The next talk will be about bio-inspired solutions for robotic surgery, and this is presented by the director of the Center for Advanced Robotics at Queen Mary, which is at the Queen Mary University of London, and the speaker is Professor Kaspar Althöfer.
Hello, IROS 24. Thank you very much for coming to my presentation. I'm from the Center for Advanced Robotics at Queen Mary, and my name is Kaspar Althöfer. And under the title Translating Nature, I would like to speak about where I take inspiration from nature, from biology, to develop systems for robotic surgery. So let me talk at first about where I take inspiration from. First of all, I look at the octopus. I think it's an amazing animal. Looking at the tentacles, looking at the whole body, there is no bone inside, so just muscles and soft tissue. And still, this animal is capable of moving around, applying high forces to the environment, capable of changing the stiffness in the various arms, in the 8 arms of the octopus. But I also take inspiration from another area, and here I'm showing a snail, and in particular I'm interested in the way the eyes are moving out of the snail head, and effectively the inspiration, or what I'm interested there in, is the idea of something that is growing from the tip, a tip growing example in nature. But also in the same kind of way, I look at plants, again something that is growing from the tip. And Barbara already talked quite a lot of plants, so I have a more simplified view here. So I would like to see how we can take this inspiration to create now medical tools. And before I go there, just a quick recap of what is currently happening in the area of robot-assisted surgery. And here is an overview. The field is very quickly changing. Only a very short while ago, this table looked quite different. The market is very, very tight, and many companies disappear very quickly. At the moment, and looking in particular on the left section of this table, there is Intuitive Surgical. They have been around for 25 years, and their Da Vinci robot is definitely a market leader. I would also highlight in this context Medtronic, who have brought Hugo onto the market, and there's CMR with another system that is being used for minimally invasive surgery. So just a few views of these systems. So here's Intuitive Surgical with their Da Vinci system, and as you can see, these are maybe not so much inspired or robots so much inspired by biology, so rigid component robots that have very rigid, slender tools that are then being used for operation through a teleoperation console as shown here. And also Medtronic brought to the market Hugo very recently. And again, we see a very similar picture there. So that is what companies currently developing and trying to bring onto the market or have already in clinical use. One more example is UK-based CMR, who are also coming with a new system there. But again, it is really the same approach that has been taken here. Very rigid component systems are being deployed for this purpose. So I have to step back a bit in time, looking at what we have been doing. So we have been looking at soft robotics for minimally invasive surgery, really radically moving away from the standard approach, and very much also based on the seminal work done in the framework of EU project Octopus, and Cecilia is here today, so we really borrowed a lot from there and try to move now these ideas forward to develop robots that can go inside a patient and conduct surgeries or diagnostic tasks. So on the left-hand side, we can see the structure there. We are going through a incision through a port inside the human body. That is the idea in minimally invasive surgery. And in our case, we then wanted to develop and have developed a soft robotic structure, pneumatically actuated, made from silicon rubber. And I want to show here now what we have achieved during this project. And you can see our device that we developed in the middle. And for comparison, we have standard laparoscopic tools. And at the end of the project, we were able to develop a device that was small enough to fit through a trocar port, so 14.7 millimeters. And you can see here one of our prototypes made of 2 segments that could be controlled individually and then equipped with a camera and be used inside the human body. You can see here one of our stiff flop manipulators moving inside a phantom of an abdominal cavity, and a camera is at the tip, and you can see on the left-hand side the camera images being fed back. And I think we left quite some legacy. There are quite a few researchers even today referring to the stiff flop manipulator. And within our project, we were also able to go inside a human. It was a cadaver study, and that was under the auspices of colorectal surgeons Alberto Arezzo and Joachim Minsk. And we could show that our system could move in a very dexterous way inside the abdominal cavity and bring back images from there in a way that hasn't been done beforehand. And I would say we were first there in a human cadaver, using a soft robot with the purpose of carrying out a minimally invasive task. But work continues, and it's great that Helge Wurdemann, our moderator here, is here today, and he is continuing this work. Yeah, let's see whether we can go back and get this video started. So now, as we saw in earlier images, the structure was reduced from 14.7 millimeters in earlier videos now to 9.5 millimeters and even 7.5 millimeters. So there is lots of scope now to use this kind of approach in minimally invasive surgery. And also, the project, the work we are doing is now the foundation for another project that has recently started, EU project Palpable, where we now again develop a soft structure. The soft structure is at the tip of our shaft. So here we have a stiff flop-like manipulator with a tactile sensing tool at the tip. And the idea is to give the surgeons a tool to palpate tissue and to diagnose where cancer is within a soft tissue organ. But we also looked into structures that really mimicked the stiffness controllability in an animal, the octopus, and we developed these tentacles. They were made of fabric and could be inflated. Using then tendons, we could move the structure in different directions, and this is an inherently antagonistic approach because the air is pushing in one direction, and with the tendons we can pull in the other directions, and in this way navigate and control the stiffness at the same time. We also learned that these structures are very good at growing. So as you have seen, the structure can grow from a very small volume into the space that we want to explore. And then we can use the tendons and control the pressure to achieve very natural, very lifelike motion, as you probably can appreciate in this video. And once the task is done, we can then deflate the structure and move it out of there. I would say very early growing robots there. And we were able to turn this then into an inflatable endoscope, very dexterous and at the same time squeezable, so capable of going through very narrow openings. Now I move to the other inspiration I earlier talked about, so the snail eyes and the plants. And here we are looking now at what is called inversion robots, tip-growing robots. So we are taking a different approach from Barbara. So we are looking at these fabric sleeves that are actuated by air, pneumatically actuated, and they are folding effectively inside out at the tip. And this is explained on the left-hand side. So in the diagram, you can see from the top, air is pumped into this sleeve that is folded outside in at first, and then it folds out in the other direction from the tip. And obviously one has to mention in this context work by Hawks and Okamura, who have been working in this area for some time and have developed these kind of inversion robots for many different applications, including also medical applications, and you can see here an intubation device. Work has been also carried out in other areas, and I would like just to show these three videos here. The one on the left is unfortunately not running, so we have here work by Valdastri looking at magnetizing an inversion robot and then move it around using the magnet. So we have elongation and movement in different directions. We have also the work by Bergeles, the MamaBot, highly miniaturized inversion robot that can even go into breast ducts. Work by Rio at the bottom. Here we look at the problem of moving the inversion robot back again. It's quite a challenge, but he has made quite some advancement there and found a solution to allow elongation and retraction. But many challenges are ahead, because this is now a tip-growing structure, and the question, one of the main questions is, how can you now attach something to it? How can you attach something that is always moving at the tip, and there's no real tip because the tip is moving all the time? So we are proposing what we call the soft cap that allows us to integrate now sensors like a vision sensor, as you can see here, and also in this video we can see it in action. So one of our larger robots with this cap at the tip is capable now of moving forward, transporting sensors, and at the same time still can squeeze through very narrow openings. Now let me quickly come to also our recent project. So this is an ERC Synergy funded project, and here with colleagues Arezzo, Ursulan and Siciliano, we are looking at developing a new system for colonoscopy, and that is very much based on the idea of the inversion robot. So under the heading of endotheranostics, we have started already very recently. We are planning now to create a inversion robot structure that can go inside the colon to develop new colonoscopic approach. And the idea there is to bring the operating theater to the inside of the colon to diagnose cancer and also to provide therapy. And so you can see in this very fast video the Inversion robot moving in and then various tools being brought in along this channel that we create, and these tools will be then there to operate on the cancerous areas once detected. I have to, of course, highlight that this work would not have been possible without very generous support by major funding sources, and I give an overview here, in particular endotheranostics and palpable through EU funding, and also the work would not have been possible without the great help from many PhD students and postdocs over the time, so I want to acknowledge their support here with that slide. That brings me to the end of my presentation. Thank you very much.
Thank you very much, Caspar. It's always fascinating to see these new technologies emerging from the lab and finding their way towards applications in the medical field. Our fourth speaker will talk about building on nature's collective intelligence, and he is leading the lab at the Designing Emergence Lab at Harvard University. Welcome, Justin Werfel.
All right, thank you. It's an honor and a pleasure to be speaking here. So I want to tell you 4 very short stories about collective intelligence. So I'm going to be talking about systems of many limited and independent components that together do something beyond the capabilities of the individuals. So take, for example, there are 2 kinds of questions, I want to say, that we ask about these kinds of systems. The first is sort of forward questions. So take, for example, a set of agents, let's say mound-building termites, and the thing that they do together, let's say building a mound, and we want to ask how do the actions of the individuals lead to the collective outcome. And then the other set of questions are inverse questions. So let's say we have, for example, a robot construction team, and we have a particular thing that we want them to generate. And the question here is how do we come up with a set of rules for the individuals to follow that will produce that particular thing. And the thing that makes this difficult in both cases is that everything is a big mess, to use a technical term. Everything is unpredictable and limited and unreliable and unknown, and there's a lot of chaos, and we have to somehow impose order on it. So the question is, how do you coordinate the activities of all of these limited and independent agents? So I want to tell you, as I say, 4 very short stories about different systems. 2 of them are natural, 2 are artificial. And I'm going to try to say something general and generalizable about each one. So the first system I want to tell you about is a set of construction robots inspired by mound-building termites. So we designed these robots to be limited in ways that we think of the termites as being limited. And in particular, they are not talking to each other. All of the coordination that they're doing is through manipulation of the shared environment. And this, in social insects, as you've heard, is often called Stigmergy. So the big principle that we use that made this possible is for the robots to use the environment around them, and in particular, these blocks that they're building with. So in addition to building with the blocks, they use them in 2 other ways. They use them algorithmically, so they look at blocks in their local vicinity and use that to help them decide what to do. And they also use them physically. Right? So the blocks are mechanically designed to make the job of the robots easier. So they do things like slide together into precise alignment, even if they're not put together very precisely. And so these, again, unreliable and imprecise robots can reliably build the structures together. And so in the end, we're able to come up with essentially compilers where we can give the system a picture of what we want them to build, just a high-level representation, and it generates rules for the individual robots to follow that are guaranteed to produce the particular thing we asked them for, again, despite all of these limitations. And so that's sort of on the theoretical side, and then, as I say, we can make it work in the physical lab by, again, designing the physical system to make the robots' lives easier. So, through building that system, we actually later had the opportunity to go study the mound-building termites that originally inspired it. So here you've got systems of millions of, again, limited insects that literally blindly together build these huge complex structures. And the sort of conventional wisdom for how they do that since 1959 has been based on the idea of a cement pheromone. So the idea is that one termite will come along with a blob of soil and put it down, and it has put some, it's working? It's put some cement pheromone into that soil, and then another termite will come along and encounter that pheromone and respond to it by putting down its own blob of soil. So that accumulates in a positive feedback loop, and then mumble, 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 and then you get a termite mound out of it. So we went to Namibia to try to fill in that middle section, try to understand better how the one leads to the other. And it turns out that there is probably no such thing as a cement pheromone. So why I say that is a longer story than I have time to tell, but we were left needing to find other ways that the termites use their environment to coordinate their activity. So for instance, it turns out they pay attention to the shape of what they're standing on. Of course, as they build, they're changing the shape of what they're standing on. They pay attention to spatial changes in humidity, especially near the surface of the mound. And they pay attention to what other termites are doing. So if a termite comes across others digging, the more termites who are actively digging, the more likely it is to stop and join them. And that study in particular, this third one I mentioned, really forced us to think differently about what the termites are doing and about the whole construction process. So the thing that attracted us to the system in the first place is the mound building, right? So we're very focused on the deposition, on where the termites are putting stuff down. But it seems like the termites themselves, to oversimplify and anthropomorphize, the termites seem to really care only about excavation. They really like to dig, and it could be that the whole mound, from the perspective of the termites, could just be a byproduct of them needing to have a place to put the soil they're digging up. So not what we expected to find when we went there, but sometimes studies of robots lead indirectly to learning unexpected things about biological systems. So the third story I want to tell is another collective construction system. So this is about beavers. So they live and build in colonies, so again, collective. Most famously, they build dams. They build a number of other kinds of structures. And the two that I want to focus on are trails, which is when they're clearing vegetation from land, and canals, which is when they're excavating a channel that water can flow through. And both of these are things they do at much larger spatial scales than the actual than the dams that they're most famous for building. So it can be very difficult to observe the building of a dam. The beavers are shy, they're nocturnal, they're often underwater, and the initiation of a dam is a rare event that can occur anywhere in a large area, and so it's very difficult to catch. So, if you're Jordan Kennedy, you take some drones and other equipment across Montana, and you survey kilometers of streams every few days, and you observe this large area where there are dozens of beaver colonies building dozens of dams. Because in this area, it's mountainous. Over the winter there's snowfall, and then in the spring it melts and there's a storm surge, right? And or a melt surge, I guess. And that washes out old dam construction, and so they need to do a lot of rebuilding. So you wind up with this very high resolution in both space and time set of maps of the whole area, and you can extract features from that, and you ultimately have this very rich data set that lets you start asking questions like what in the environment affects when and where beavers choose to build. So the classic answer to both of those questions is all about the sound of flowing water. So the story is that when and where beavers hear water flowing, that's when and where they build. That obviously can't be the whole story, because if that was the only thing they were paying attention to, they would spend all of their time trying to dam up waterfalls. And they don't do that. They're smarter. They wait for the water flow to subside over the course of the summer. And they wait until it's low enough that they can actually build a dam without it getting swept away right away. That is, they're not building dams all the time, and eventually they stop getting swept away. They're waiting until it's safe to build. And the interesting thing is that you don't see that if you just look at the dams. So here, for this table is showing for a few different colonies. This is the flow rate when we first saw dam construction and when we first saw trail construction. And dams are scattered all over the place. And if I show you a similar table with dates or with...
Gentlemen, for number 4, Robotics in Africa, will start at 3:50 p.m. in plenary room hall number 1. Thank you.
Excellent. Okay. Everything, whatever you look at, things are scattered with no clear patterns across colonies, except trail building always starts within a fairly narrow range of flow rates. So trail building precedes dam building. We think it enables dam building. This is where they're getting the material to build the dams with. And so the beavers are waiting until the conditions support it to start preparing for building the dams. And again, I think the important thing here is that you have to look at the bigger picture beyond the dams in order to see this. As for canals, canals are something that colonies work on across a time scale, across generations. And active canals get excavated further, inactive ones silt up, and the whole thing winds up looking, I think, very much like an ant foraging network. So you have stigmergy happening on this very large spatial and temporal scale.
Gentlemen, for number 4, Robotics in Africa, will start at 3:50 p.m. in plenary room hall number 1. Thank you.
And this is the first time I'm aware of seeing this kind of stigmergy then in a non-human mammal. And the canals are essentially telling the beavers where to build. They build dams, not dams, especially trails. They build very close to the canals, and when a new colony moves into an area, it finds a place with canals and settles there. Okay, last story I want to tell you is about cooperative manipulation. So you've got a bunch of robots moving a large thing together. And I feel like most work in this area falls at one end or the other of a spectrum. So at one end, you've got studies of things like natural systems that tend to be very phenomenological, right? So you can say things about what happens, but you don't necessarily have a lot of control over the system or performance guarantees. And at the other end, most studies, I think, take this approach of sort of heavy use of robotics formalism. And then you can do very powerful things, but the cost is that you need a lot of information. So you typically need to know things like the mass distribution of the thing that are moving. You need to know the number and locations of the robots. The robots need to be in close communication with each other all the time. And I think there's a worthwhile space in the middle for kind of ad hoc tasks. Like the need may come up for you to move something heavy. And if you need to move some furniture, you call your friends. And you just want to pick up and go, right? Or you call your robots. You don't want to have to spend a lot of time figuring out the parameters of the table and telling everybody where to stand and planning the whole thing. You just want to go. And so to start designing a controller for that, we looked to ourselves. So this is a thing that we do. So what do we do? So if you imagine yourself helping friends move a big table, you're paying attention to the way the table moves. Right, you are feeling that force on this shared object, and so again, you're coordinating implicitly through the environment, and you're feeling the way it moves also to decide whether a force, like based on its length, is intended as a signal by the leader for the object to move in a different way, or whether it's a transient perturbation that ought to be rejected. And if the table moves suddenly in an unexpected way, you stiffen up, right? You want to make sure that it's stable, and then once you're sure of that, you can start to relax and let it move again. So that was the starting place for the controller that we designed for this. And then you can do, formalism to it and do things like prove stability. But the point here is that, bioinspiration, like the traditional strength of it is it provides a proof of principle. And so that is often a good place to start when trying to design a system. So, 4 short stories. These are maybe the morals of the stories. And I want to close then by thanking all the people who made all this happen. I've color-coded them according to project. And I am looking forward very much to this discussion.
Thank you very much, Justin, for these very exciting insights of how animals can create and change in the environments, for example, building canals on a big scale. I think that will feed nicely into our session now, and now we have time to debate some of the aspects of biorobotics, and also if you like to think about questions to the panel, we will probably have time to take a couple as well. I'd like to start really with Barbara. You mentioned sustainability. And the theme for this year's IROS is the next generation of sustainable robotics. So some of you might have heard the breaking news: Google turns to nuclear to power AI data centers to really cut emissions for their extremely energy-consuming data centers. So you were talking about energy efficiency. Sustainability covers more than that, I believe. So what can we learn from biology, from nature, to really make an impact, a positive impact, and look into maybe also long-term sustainability?
But I think that this point that you mentioned, so energy efficiency, is really a crucial point, because the current technological solutions, at least most of them, are really energy demanding. So, and nature can help us in redesign our robot, because of course living creatures have to save energy, otherwise they die. And so, based on this simple, effective principle, we can really rethink how we can design our robot. As I said, starting from the design, we can reduce the energy consumption. So then, of course, you can supply energy for many of the tasks that the robots have to perform. But if we reduce from the scratch, when we design our robot, we can first of all improve on the sustainability, because we can reduce the energy needed for the robot. So this is the first point. The second point, we need to reduce also what is called e-waste, so electronic waste, because we produce a lot of technology, but then if they are not reusable or biodegradable, of course we affect the quality of our planet. So it's very important from my point of view, in terms of materials, in terms of electronics, of course the energy that we supply to our robot. So there are groups, other communities that are working on biodegradable electronics, a new form of batteries. So we need also to cooperate and collaborate with these other experts in the field in order to improve the performance of our robot.
So now, maybe to Justin and Auke, so the generative AI tools like ChatGPT, but it's not only ChatGPT, use a lot of resources. What can we learn, or what can you bring from your research to maybe reduce that?
So, shall I maybe start? Yeah. So first of all, indeed, I think we should look at animals. Like if you take an eel can cross the whole ocean, 3,000 kilometers without food.
It loses half of its body mass, but super efficient locomotion. So there we should really aim at the same type of efficiency. Same from our brain. What is it, 25 watts we use? It's really super powerful. And I think neuromorphic computing, as we heard yesterday also with Davide, Scaramuzza and others, I think we need to push also for implementing these principles in chips. And then I think on both sides we can win and be much more energy efficient. So.
Justin, I throw the ball over to you.
Sure, I apologize if I'm repeating something because I literally could not hear a word of that on this stage. But I think the role of bioinspiration here is to give us, again, a starting place. So if there's a thing that we want to do and there's an existing natural system that does it, it's already undergone a lot of optimization to do things well and efficiently. And we know also that it's easier to learn to do a task if the body plan is well suited to the task. And so again, I think the more we find examples in nature to guide our starting points, sort of the less work it'll take to get to where we need to go.
Yeah, maybe to add, I mean, I completely agree with what my colleagues are saying here. Maybe it's okay to throw in the term embodied intelligence. And I think that is something that we see also very much happening in biorobotics. We take inspiration from the environment, from nature, and they have shown, these animals have shown that they are very well adapted to the environment, so a certain type of body intelligence is already there. And it's already shown that by using that, we can create better systems, better robotic devices, and also those that are less in demand of computing resources. So I think that is a good approach forward, looks more at sustainability, and I would also argue creating now nuclear plants to make ChatGPT run is the wrong approach. I think we should see how we can at first think about a more sustainable green approach to things.
Yeah, I like your thinking, and I want to go along these lines, but remind everyone at the same time to come, if you have questions, please raise your hand and we will come with a mic to you. There was last week a report by the Tony Blair Institute for Global Change released, and the report was talking about the advancement in technology, which is very much dedicated to the improvements of, or the advancement in generative AI. But it at the same time talks about what you said is embodied intelligence and the gap between AI and robotics, where robotics really have to advance to come almost on the same level of AI and then merge and come together in what has been phrased over many years, embodied AI. So maybe Barbara, maybe you can comment on this. So what are your thoughts on that?
I think that, of course, AI is important. More and more the trend is to combine, as you say, the AI and robotics to improve the functionality, and the task that our robot can do. And this is for sure one of the future trends. But I think that we need to think again to how we can implement more intelligence in the morphology, because it's a part of the task. So part of the control is demanded to the morphology and how the system, both natural and artificial, interact with the environment. So this is part of the intelligence, in addition to the control, in addition to the AI. So we need first to optimize, from my point of view, this part before including AI. Also, AI is important for many tasks, but not for all. So in some cases, using more simplified control, it's enough for most of the tasks that we are implementing.
Maybe just to add, I completely agree again. And my feeling is we are at the very beginning of embodied intelligence. Much more work has to be done. We have to develop more of an understanding on actually how to create these fantastic, efficient systems. And I would also, and I completely agree with Helge, I think AI and robotics has to come even closer together. There's too much of a separation yet. But also I would request from AI to look at the embodied intelligence aspects, because at the moment AI is not very efficient. Nuclear plants are needed to run ChatGPT. Why can't they create something that is efficient as a human brain, for example?
So how could, some of your research is not only looking into biology and the inspiration, but you are talking also in your work about, feeding it back to understand more about the neurology of the human. So how can that help?
Yeah, I think here, robotics has really a big role to play. I think we know how to put things together. We know how to analyze systems that have multiple components. And that's really key to help neuroscientists to understand the interaction between all these components that are highly nonlinear and everything. So I think there's an enormous opportunity to do science with robotics. And here we should just do it properly. And maybe there's a message for young people in the room, is if you write a paper in Biorobotics, either you should make it as an engineering paper, where you should have a benchmark and estimate performance and hopefully have a better performance than other approaches. So that would be a super good biorobotics engineering paper. If you go for science, the good news is you don't aim at performance, you just aim at having good hypotheses, scientific approaches, experimentally iterate, and it's a completely different way of writing a paper. And it's good to know which one you write, because if you're in the middle, I call that the valley of death. You don't contribute to science, you don't contribute to engineering, so don't be there. But there's really an opportunity to do science with robotics, and we see it with many high-impact papers coming out in Nature and Science with robotics as a tool.
Yeah, thank you also for mentioning this. I think this is a very important point, especially for the upcoming researchers. So now, all of you have done fundamental research and fantastic and mind-blowing fundamental research, learning from nature. And you presented applications, potential applications. I feel like there are quite some hurdles that we need to overcome, some challenges, especially in the medical field, to really drive now engineered solution for applications. Justin, may I ask you maybe to comment on this? Where are the big hurdles to now take the engineered solution of our inspirations to then translate them?
I think some of the biggest hurdles are in things that are meant to work in the natural world. Like a lot of what we care about, I guess, is systems that are designed to work in human-designed environments. And those are very controlled, and there's, we can put, boundaries on what the robots are going to encounter. But I think if we want to do things in the natural world, and I think we all do, that is much harder to deal with. Things are much messier and less predictable.
And when we look into robotic hardware, are we actually there? Do we have the dexterity in the hardware that we need to deliver real bio-inspired solutions?
I mean, that's a very good point. I mean, I think we are far away from what animals can do. I use the octopus as an example. Fantastic dexterity, can control the stiffness, and even though there are no bones inside. So I would argue, first of all, we are very far away. Human hand, another good example, very far away from that. But also, we should maybe not necessarily try to translate everything we see in nature into an engineering solution. I believe we should take inspiration and then see how we can, come close to that performance, possibly with a solution that is slightly moving away from what us inspired in the first place.
Barbara, do you have something to add there?
Yes, I agree. I think that, of course, it's a simplification, it's not a copy, but we need to implement the principles. So in order to really have robots that can operate in unstructured environments, because we can really open completely new scenarios of use if we are able to implement this capability to cope with uncertainty in our robot. Because also moving inside a body, it's an issue because you don't know how to sometimes not to move or to explore some part of the body, and even in other environments. So we can open new scenarios, new markets in the future, but we need to implement the basic principles of the system that we imitate.
Yeah. So that leads us a little bit to look ahead, maybe 10, 15 years ahead. The term biorobotics, bio-inspiration has increasingly occurred in publications, in Google search engines. What do you think will be the next term in the field of biorobotics research that will be as successful as biorobotics? Auke.
Salamander robots.
Without any bias.
No bias, yeah. Yeah, no, I should think about it. First of all, I just want to add something. I think we can be super proud as a field in biorobotics because now some of the best platforms are bio-inspired. Quadruped-legged robots outperform many wheel-based platforms. The best teams doing the Subterranean Challenge with DARPA were legged-based. So I think biorobotics is already competitive and outcompeting other solutions, so we can be proud of that. And while the others answer, I'll try to find a better answer to your question.
Barbara, what do you think?
I like the word adaptation. So adaptable robots for me means, they are really, what I said before, to really move, navigate, perceive an environment. Adaptation is a form of intelligence. And so they can really adapt the behavior, the morphology, everything. So I like very much this concept.
Okay. Caspar, will it be endotheranotics?
I don't have a crystal ball, so I don't know where we will be in 5-10 years, but I think we discussed it earlier, moving AI, computer-based intelligence closer to the embodied intelligence. I think that's where we are heading. I think that will be coming, where we have really a fusion of these technologies.
Okay.
And I think as far as the question about terms goes, biorobotics and bio-inspiration don't need to go out of style. I think there's a lot left to be mined there.
Okay. So thank you very much for sharing this. And this is all we have time for today in this keynote session. All speakers will, of course, be available after the talk and throughout the IROS 24 conference. But before the next session starts, and one of them will be in room 1, as we heard during the talk, please join me in thanking all of the speakers: Barbara, Mazzolai, Auke, Isbert, Justin, Werfer, and Kaspar Althöfer. Thank you.
Let's do a big round of applause for Helge. You are a fantastic chair. Yeah.
Welcome to the AI Olympics with Real AI Gym competition at IROS 2024 in Abu Dhabi, UAE. In this competition, we want to benchmark various learning and control algorithms for athletic intelligence in the real world. In particular, we have developed a double pendulum system which can be used as both Acrobat or pendulum, and the task is to go from a downright configuration to the upright configuration by using only one actuator. And this is a particularly challenging control problem because it has chaotic dynamics, and one has to use the controls available to you in an intelligent way to go from this downright configuration to the upright configuration. And we have 4 teams competing that qualified for the simulation phase of the challenge, and then they participated in the remote hardware phase of the competition, and now they are doing the on-site competition with us here in Abu Dhabi. And we have a benchmarking suite where we have implemented some cost function which evaluates the performance of different controllers in a unified setting. So what we do is, when the robot is swinging up, we apply randomized external disturbances, and we check the robustness of these control methods by checking out of 10 trials how many times it succeeds. And this is the main goal in the challenge at this stage. And I'm happy to show you the system next and talk more about it. And when the task of the system is to go from this configuration to the upright configuration. So that's what teams are competing for. And when the teams are doing this, we apply some randomized disturbances to the system, and a robust controller should be able to deal with these external disturbances and still succeed with the swing up task. Now behind me you can see the double pendulum system that we have implemented. As you can see here, we have 2 actuators on the system, and one of them can be used to drive the system, and the other one is used as an encoder. That means it's passive, and we use the encoders to measure the state. Right now you see the Acrobat hanging in the downward configuration, so this is the starting configuration. And when the task of the system is to go from this configuration to the upright configuration. So that's what teams are competing for. And when the teams are doing this, we apply some randomized disturbances to the system, and a robust controller should be able to deal with these external disturbances and still succeed with the swing up task.
Mohammed Faye. I'm from RIT Dubai. Today we are here to participate in the Falcon Behavior Detection Challenge. And in this challenge, the task is to detect the behavior of the falcon and understand their positions in a designated area. As you can see here in the screen, we have the coordinate of this bird according to X and Y, Z. And we have different challenges every day, and we develop our program to detect the birds according to the challenge given by the organizers. Thank you so much. All good?
Welcome to the Falcon Monitoring Challenge. In this challenging, we are trying to track the wildlife, in our case the falcons, and how they behave when they are within the cage. It's important to understand the difference between the animals, understanding... Should I start from the beginning? Hi, welcome to the Falcon Monitoring Challenging. In this challenging, the objective is to track the different falcons and how they behave while they are on the enclosure. Each falcon has their own identification, and some of them are more active than the others. So with this challenge, the teams need to use the cameras to be able to track and identify each one of the falcons and understand what was their movement while they were in captivity. That way, could help the people to select the right falcons to take to the hunts or for exhibitions. Thank you.